Hey, so we're going to start looking at our last unit, which is Unit 9. And Unit 9 it's called the application of thermo. So we'll see delta H, we're going to see delta G, and we're going to see delta S. And that's what we mean by thermodynamics, the dynamic of this heat exchange and spontaneity of reactions. And our new friend, which is a good friend of mine, is entropy, which is going to be delta S. And today's lesson is an introduction to entropy. And we'll also talk about absolute entropy and entropy changes. So I'm going to share my screen. And we are going to do entropy. All right. There. All right. So I've heard someone say one time, it was a chemistry teacher, she said, every time you walk in a room, do you think to yourself, the entropy in the room has just increased? Okay, so let me explain to you what this word means. And its symbol is delta S. So obviously this is the change in entropy, right? That's what we will be concerned with. What is entropy? Entropy is a measure, and I'm going to keep this simple, of disorder. Okay? The more disorder, the more entropy. Okay? Now, what do we mean by disorder? Because even though I get to use the word disorder, you may be better off not using that word. One of AP's things. They want to realize that you know that disorder is, a great disorder has a large amount of microstates or microstate possibilities. Very random, but I don't really want you using that word either. I just want you to understand many different arrangements or microstates. And I personally think that for your exam, the term microstates is probably a better term. Entropy is hard to explain, okay? Now, let's talk about relative entropies for a minute. That might help. And it is true that solids are more ordered than liquids and therefore have less entropy. The particles in a solid have less available microstates present. Liquids have less entropy than a gas. Okay? So as you increase the movement of those particles and they begin to roam around, there are many, many more possibilities of arrangements of particles. That's what I'm going to write right here. Possibilities of arrangements. That's good. Of particles. That's the phrase I was kind of looking for. That's what I mean by more microstates, more possibilities of arrangements of particles. That is a good thing for you to say, right? I learned it's more disordered, But that is what disorder means in this situation, okay? Now, solids are, gases have more entropy than do liquids and do solids. Right, solutions, when you take a solid and you make it aqueous, right, you are increasing your entropy, right? We have an increase in our change in entropy, right? It goes up. So we could talk about processes. Now, substances have been assigned entropy values, and you can look in an index and find those values. Just like you can find the bond energy values for a, breaking an oxygen and oxygen double bond, you can look up entropy values for certain substances. It is always based on their state of matter and the form that they are in, right? They can be compounds or it can be elements. Elements do have an entropy. Entropy values actually are based, dig in these colors, you guys. Entropy values for substances are based on a perfect crystal at what temperature? Absolute zero. Zero. Oh, that's not such a great color. I'll change it. Entropy values for substances are based on a perfect crystal at absolute zero. Okay, so a perfect crystal at absolute zero. Look at there, I'll fix that for you. Absolute zero, absolutely no movement of particles, perfect crystal, a perfect arrangement, absolutely no other microstate available. That is defined to be zero entropy, okay? All other entropy values are based off of this. Therefore, all other entropy values are positive. Okay? Now, in your notes, it states that sometimes ions are given negative entropy values. You probably won't run into it. If you do, don't be freaked out. It's just a zero is on a different scale. Nothing more said about that. But for the most part, all of our entropy values will be above zero because zero entropy is the basis, and that is a perfect crystal at 0 kelvins. Don't get that very often, right? Okay. So that is my introduction to entropy and absolute entropy. Okay. Now, when you will look up your absolute entropy values, and they have been assigned, right? Like we were talking here. We, however, will be more concerned with the change in entropy for a given process and being able to predict if a given process has an increase in entropy or a decrease, in entropy. Okay, that is going to be a big focus of our application of entropy, right? If entropy increases, we become more disordered. And if entropy decreases, we become less disordered, or we become more ordered. All right. Now, we are also going to talk about spontaneity. Now, it is the case, guys, that in nature, the second law of thermodynamics. Wow, that sounds serious. Whoa, that's serious. The second law of thermodynamics. What does it state, guys? Sorry, I'm over here looking for different colors. Let's see if this one works. Nah, let's get a brighter color. once again, sorry, I'm playing. Second law of thermodynamics. You might be thinking, well, what is the first law, Miss Murphy? It is the law of conservation of energy. All right, well, the second law of thermodynamics states that the entropy of the universe right? Not the system, not the surroundings, but everything. The system and the surroundings make up the universe. So in every spontaneous process, in every process, the entropy of the universe is increasing. Now, I need you to realize that this says universe. We won't be talking about the universe. We will be concerned with the system, and we will see both entropy and entropy. We will see it both increasing and decreasing. But the system is not the only factor here. The surroundings are also a factor. So the second law of thermodynamics is for the universe. We will be using the system. And for a system, we will be using delta G to determine whether or not it is spontaneous. And we will see that entropy is a big factor there, but not the only factor. Okay? Now, how can we calculate changes in entropy? Well, let's look right here. It's easy. We're almost finished here. Oh yeah, I just thought of something else I need to say. So the enthalpy change for a reaction, not the universe, the system, is equal to the sum of the entropies of the products minus the sum of the entropies of the reactants. And you might want to write these R times the moles, right? So the mole, the way it's balanced matters, okay? Or you can predict whether it will be a positive entropy or a negative entropy, right? We're going to apply that real quick. Let's say, so when predicting, you want to look at states of matter. In both reactants and products, right? And apply what we talked about, right? Do we have solids turning into gases? Well, gases have an increase in entropy. Let me finish this. I hate it when I start writing crooked too. I'm going to let it go this morning. I'm going to let that go this morning, right? So if I see that I have a solid reacting with a liquid and I produce, a gas and a liquid, well, I've increased in entropy, right? Because I have, just look at my particles. Gases and liquids have more entropy than solids and liquids do, right? Once again, if I have a solid and I dissolve it, I have an increase in entropy. But if I have something dissolved and it precipitates out, I have a decrease right there, right? If I have a gas and I have 3 moles of a gas here and I have 2 moles of a gas here, well, then I have lost randomness. I have lost particles that will create more randomness, and vice versa, right? If I have 2 moles of a gas here and 3 moles of a gas here, then I have increased my microstate possibilities. Okay, those would be the vocabulary I would encourage you to use. So I can predict, and you need to be able to do that, or I can calculate, and we will also have to do that. So what I've done is notice in this practice problem, it says calculate. It's not letting me write on it. I don't know why. That's weird. Calculate delta G for this reaction. We're not calculating delta G because that's not this. But in order to calculate delta G for this reaction, you have to calculate delta S. So we are going to not do what we're being asked to do, but rather we are going to calculate delta S. Okay? And the reaction is 2CH3OH liquid plus 3O2 gas. Oh, that looks like combustion. So we should get our carbon dioxides. Yep. And notice that we've got liquid water, right? That matters. If you were to look those values up, make sure you get liquid and not gas or solid. Okay, so let's get the sum of the entropy, right, of our products. Well, that's the CO2 times 2 plus the H2O times 4 minus the sum of the entropy of our reactants. Well, that's 2 times the CH3OH plus the 3O2. Remember when we were calculating delta H values, if they were elements, they were 0 for enthalpy, but for entropy, that's not the case, right? Because there is disorder here. These are not perfect crystals. Okay, so focus, Miss Murphy. That's going to be 2 times CO2, which is given to us up top with an entropy of 213.6 joules per mole Kelvin. So I want you to notice that entropy is most often given to you in joules. 3 oxygens, look up, that is 3 times 205.0 joules per mole Kelvin. Also notice that we're multiplying this times moles, right? We're multiplying this times moles. So those moles will cancel. So we'll multiply those and we will subtract from it 2 times the methanol. It's 126.8 joules per mole Kelvin. Once again, this is your moles. And 3 times the oxygen. Uh-oh. Did I already use oxygen and make a mistake? 205, I sure did. I bet y'all caught it. This should be 4 waters here. How does Miss Murphy, I do it on purpose. I'm just keeping y'all on your toes, guys. 69.91. It's a low entropy, isn't it? And the 3 over here is the oxygen. And that is my 205.0 joules per mole Kelvin times 3 moles, right? All right, let's just add those guys up and hopefully it matches that pretty little number there in blue. That one right there. Okay, 2 times on 2 times 213.6 equals plus parentheses 4 times 69.91 close equals 706.84. Oops, that was ugly. Sorry. And then over here, 2 times 126.8 plus parentheses 3 times 209. Let's see, 868.6. 868.6 joules, like that. Okay, those units look weird. Most importantly, I need you to realize that these are joules. We do need to subtract these. 706.84 minus 868.6 equals, and I've got 0. negative 1618. Now that's joules Why do they have oh, they did delta G per mole. Oh, I just assumed my exponent. Sorry. I've got 0 point negative. Oh, let me put that in scientific notation. Negative 1.618 times 10 to the second joules per Kelvin. Notice and up top, they've changed that to kilojoules. And you are going to want to get in the habit of doing that. And you can do that by dividing it by 1,000. And that is because we will often use this in conjunction with enthalpy. And our enthalpy is in kilojoules. And we will use our entropy and our enthalpy to calculate our delta G. And one entropy is given to you in joules. Enthalpy is given to you in kilojoules. So you might want to go ahead and get in the habit of changing this to kilojoules, or just being very mindful of your units throughout this, okay? All right, that's going to end that. Adios. No, let's look and see if that makes sense. So what I see is a very, very, very minimal change here, 0.16. So we should be able to look up here at our states of matter and see, all right, oops, I don't want that. I want a highlighter. And let's see, we've got a 2 moles of liquid, 3 moles of gas, to 2 moles of gas and 4 moles of liquid. So we do see that we've produced a little bit less gas than we started with. So I would think that we would gain a little bit in our order. We would have a negative delta S, right? We would gain order, lose entropy. That's negative. And in fact, what we see down here is a very slightly negative value. So that makes sense. You want to think about those things. Now we can say bye. Bye. See ya. Excuse me.